do have an overlap with the last talk. Slightly different perspective on a few things though. And first of all, I just want to also reiterate how enjoyable this meeting has been. I've been here a couple of times before, and it's I think one of the things that's worth remembering about these meetings is that in a sense we continue and we keep in touch after the meeting. Certainly the things that came out of the last two times I were here really sort of got into their stride almost 6 months down the line. So model coupling. I was asked by Peter to do this. Peter knows Peter here knows I'm a bit of an evening person. So giving a talk first thing in the morning, somehow it's like, well, how long is a piece of string? So, model coupling. I said yes. We'll do our best, and do stop me if you want to. So to sort of say the obvious is, if you have a single model, you often have drivers, goes into a model, and you have outputs. And then, unlike Anna, I perhaps think they're coupled in the second row if the outputs of one model 1 then drive model 2. And I think you might well say that coupled models with feedbacks are where you get an interaction between model 1 that can then into model 2, feeds into model 2, but actually there's a sort of link that then goes back to model 1, and so this sort of circularity in the bottom part affects outputs. Now we often get very excited by feedbacks, and we often talk about positive and negative feedbacks in the climate system. I think they are fascinating, but they do sometimes do some strange things to the coupling itself. So just to have a similar slide to Anna, this one's come from NASA. These are all over the place, these slides of course, but they do say a tremendous amount. And I think that climate modelers, that we've had sort of 50 years of this really, because a lot of these climate models are in effect speeded up weather forecast models. And so there is a tremendous amount of understanding, I think, about what can happen in the environmental modelling community. And so, as to sort of say the obvious with climate models, we want to know in general what's going to happen to their response to 4 drivers. One is fluctuations in solar power, the sun. One is what happens when volcanoes go off. And then the two perhaps we're more interested in, or definitely more interested in, is one when greenhouse gas concentrations go up, what sort of world will we see into the future? And one where we change aerosols, which still have tend to be on a smaller scale, but still sort of the continent scale in their size, and they often have an effect of cooling down. They're probably to some extent protecting us at the moment. But I think the thing about climate change is what a lot of these couplings do is it's not just the case that at 2 degrees we simply have warmed up the world by 2 degrees and everywhere is the same, and you're just simply moving some sort of Gaussian distribution over slightly, and you can work out the extremes from the top of it. The couplings between the oceans, between the land, between the atmosphere, and between the ice, the sea ice and the land ice, are such that they can have quite significant impacts also on the circulation, and that the warming and the rainfall patterns are very variable, very heterogeneous. So there's this incredible amount of capability and in doing this, and of course, as we know, all these models end up in the CMIT5 archive, and then it's analysis of them that influences the UN IPCC reports. Now, one of the things that I think, as we've probably known as we've been here, is we've had some interesting weather over the last month, to say the least. In fact, we've actually just a few kilometres away from the hottest temperature ever recorded in the UK. It was quite exciting that day. But some of the weather patterns as well, I don't know if you ever watched them on the UK radar website, and these are very intricate, sort of very, very detailed, very intricate storm patterns that occur, how they're going to change into the future. Now, the weather forecasts, I think, are becoming quite remarkable. I think they really, you can look at them for the next day and you really do get a very, very good idea. You can plan your day around them. But these are very high resolution models, and say to make a 24-hour weather forecast ahead, they've often run for 2 hours to get that forecast. Now the thing is, they have all the complexity, the very high resolution, and get the storms and everything else you may expect, the convection that drives that. But if you wanted to obviously run at that scale globally for a 100-year simulation, you'd have to leave the computer going for 10 years, and that wouldn't really be very useful if you want to analyse it in the months ahead. So unfortunately, part of our job in climate modelling is to sort of take a very good model and degrade it so that it can run more quickly at a lower resolution, and you can make these century timescale forecasts. But there is a sort of way of getting around it, is that you hope that the degrading is right, which might be the, I don't think I've touched anything.
You just click the screen.
I click the screen.
Probably just move the slide for a while.
Oh, it's not the first. Okay, so I'll just keep talking. But so what you do is you have this thing called downscaling, and then the way you downscale is that you assume that the broad fluctuations are, the broad behaviours are correct. Great, thank you. I don't know what I did, but sorry. And then you have this sort of one-way coupling where you nest inside a regional model over the area of interest, and then you perhaps statistically downscale even further when you get right down to the sort of catchment 1 kilometre level. So that sort of thing is done. So that gets you down to a very high resolution. Now, when you do this, of course, it doesn't feed back, and that's a frustration because there could be things that happen at a very fine scale all around the world, and then you really do actually want them to feed back onto future change. Right, okay, so just getting into, everyone has their pet piece of software, and even I can be a bit of a software bore at times, I do realise that, but it is worth just thinking of where we've got to, and just one slide on this is, we're at what we call 4th generation software now. I think nothing is actually coded in machine language anymore, 1st generation, but 2nd generation, a lot of the weather forecasts, certainly in the UK, if you watch it on BBC, that's a piece of Fortran that's been run, and the couplings between them tend to be between the subroutines are all done extremely carefully. If you look at a piece of meteorological office code, someone has checked the couplings, you have a second signature, someone actually goes through and checks with you, and I think it's very good practice to be doing all of that, but of course it takes time and it takes money to do it. I think one of the things that, despite it all being written in Fortran, that we have in the climate modelling world is these things called netcdf files, and I think they're a very good way of communicating. Now, the thing about them is that you can put a lot of information in the headers, and that headers right down to actually annotation of who's the responsible person for this code, DOIs of data sets. I find that sort of thing incredibly useful, and that might be a language that we could adopt in time between ourselves. And then of course you've got the newer languages like Python and R, which are unbelievably flexible. I mean, to say the obvious, they're 4th generation object orientated. To say the obvious, you can move array sizes around. You can't do that with Fortran. Incredible ability to visualize things. So, and the thing I think that's so special about that is so many of these libraries exist of code that people have written. So if you're into AI, there's a whole library. Now, of course, that's a talk in itself. I'm not going to go there right now, but I think there's amazing things in those libraries we could use, but we do have to use them unbelievably carefully and understand the mathematics behind it. And then we may also want to think from this project whether there's any sort of web-based interfaces ultimately to drive models that policymakers could use. Okay, so I'm a mathematician by training, and I think it's been an interesting 25 years working in environmental science. I think someone asked me, well, what have you learnt from it since stopped being a sort of a mathematician doing fluid dynamics problems? And I think it's to learn the epsilon, the uncertainty at the end of equations. But just going back to equations for a second, you could, and particularly since you're in the Newton Institute, you could argue that in the world things can only do one of 4 things. If you have a quantity and they're linked, so they change, which is on the left-hand side, in time, they diffuse, they advect. So the diffusion is characterised there by a kappa, that might be over the free spatial scales. Advection is where something's carried by the wind speed ui, and then you have a loss or a gain term where something is dropping out the system or changing state. So what's this got to do with coupling? Well, I think you could argue that if you had 2 quantities S and T, the way they may individually diffuse and advect in different ways, for the same wind speeds, they'll advect in a similar way, of course, but the coupling is where things change state. So you could imagine a very simple example, and the whole climate system is just full of these things, but just look out the window now, and all that vapour up there is changing to clouds, and we might get rain later. So it could be just a change of state of the same gas, but there's many of these examples, but the coupling comes in through these F1 and F2, and I think one of the things that we rarely do, and it's just thinking about trying to give this talk, we get obsessed by our own sort of subroutines or our own particular model, but we rarely actually really think about the implications of couplings. I mean, this is really, I'm giving the same talk as you, Anna, in many ways, and I'm sorry about that, but So a focus at that end would be interesting. So the standard way, if you just go upstairs here, there's lying around up there is the Journal of Fluid Dynamics and various other sort of in-house journals that Newton people publish in on what you might call the standard mathematical meetings that you have. You will find virtually every paper, you don't go very far before you do some sort of scaling between the equations. And so things can, as mentioned, things can only do one of these four things, but at any given time, at the majority of places in a system, there's a balance between just two things. So the diffusion might be balancing the change, and there might be no coupling. So when you scale, you take a typical, you have to sort of use your intuition for this. And it's a funny thing, because as ever with these bits of mathematics, and similar to this meeting, I think, the further you push things, it's very mathematical, but ultimately, and I'm sure the statisticians will back up on this, you have to sort of believe in your intuition. And your intuition gives the sort of magnitudes of, say, a characteristic length scale, time scale. And when you scale these things and give them sort of these characteristic values, you find the bits that dominate and remain. Now, this is a very long, drawn-out process, often doing this, particularly if you've got multiple coupled differential equations. But the thing that's so nice about it is if you get to the end of it, you've sort of gained two things. You've gained a sense of what really matters in these equations. You haven't had to find that numerically. You haven't had to put some massive nested set of arrays, and you have to leave it going for ages. Emulation is a wonderful thing, and I built emulators myself, but this way can sort of get round some of those issues. It does allow you to have this sort of robust sense of really what matters. And the interesting thing in here would be, this is just a sort of schematic really, but if for instance for quantity S it changed in time and it balanced the coupling only, and then for the second one actually the dominant term was how the coupling interacted with the diffusion, you have a much simplified system, and you could put the focus on what's the importance of F1 and F2. So it's a mathematical way of putting an emphasis on what's the importance of the coupling compared to the internal changes to that variable. I'm going to keep using this, not this, in case we lose the slides. So an interesting time yesterday. Now the thing about combining all these variables is that you come up with, you cluster them together. So I'm sure many of you are familiar with non-dimensionalization. So these clusters all are the way that give you these balance of terms. So they're the combinations of the scaling. So the top one being the Reynolds number, that's a balance between viscosity, so sort of stickiness of a fluid, the density, length scale, and a velocity. They all have numbers after them. So I don't know, perhaps we'll end up with the Harris and non-dimensional number of coupling together social economic models. But we can do this, and I think there's just one caveat at the end of this, is when you get this reduced set of equations and you go and talk to mathematicians, they just love it at that point. You simplified it, we can really try and even sometimes analytically find solutions. I think the key thing to do in our game is to make sure you find the right mathematician who will do that, but come back and put the units back in and say, in this reduced set, you can get this set of behaviours depending on the non-dimensional numbers, and the answer is this. So they come back, and it doesn't just sort of live in maths world from that point onwards, however exciting maths world is. Okay, so what are the couplings in this? So this is a very naive plot, and I've done my best to listen in on the talks, but so sorry if I've done a disjustice here to what other people have said, but it feels to me as if there's relatively little coupling between landscapes next to each other. Now you can shoot me down at when it gets to half-past and we all talk together, but the link at the bottom is relatively small. But UK policy is from the top left, the blue lines down to Farm 1, Farm 2 could actually be quite strong, and that's the thing in a sense we're talking about at this meeting. It's a two-way coupling as well, because what we learn, again perhaps from follow-ons from this meeting and as we engage stakeholders, is it feeds back on UK policy. At the same time, we're going to feel the effects of climate change, and there's someone somewhere has got to work out whether what happened a week ago is going to become more common, and whether extremes are accelerating away faster than the mean warming. That's going to have a lot of effects on what we do at the land. Even if you end up at 2 degrees, there could be something significantly different for the UK. But what would be really exciting, what would be the really exciting thing to come out of all of this, and I think it's if we came up with a coupling at the top between UK policy and global policy. So the reason that there's no link here between Farm 1 and Farm 2 and global policy is because under Theresa May's thing about can you all work out how feasible it is to have net zero emissions, even if we do that, and to say the obvious, other countries don't, then we'll have relatively little effect on climate change. But what we could do is, if we show it all works, is that this meeting and things that follow on become a sort of exemplar of how a country could do these things. And so we hope that somewhere down the line that by showing it's possible, the coupling at the top, the red curve, which is nice and thick, I think Paul and Blair, you'll be pleased to see, maybe one day that will emerge and we can think back to, I remember when we all spent that month in Cambridge. Right, so propagation of uncertainty. So one thing that I think has come out of this meeting is a lot of people saying there's propagation of uncertainty. So I was sort of challenged to put one slide in that's slightly provocative. And I would argue that we could say it's all too difficult. Right? We could say, don't worry about even the couplings. We don't even understand what's happening to the individual models. The parameter uncertainty is huge. We can't pin it down. We don't have the right data. So we could argue that none of this environmental modelling, particularly sort of things we've been thinking about at this meeting, is feasible. The third bullet point is we could say we think we know precisely what's going to happen and ignore uncertainty, take the mean parameters, and rather naively go and talk to the press or however we go on Twitter and suggest that we know exactly what's going to happen. And I think the environment may change so fast that we could soon find out we're wrong, and that will come back and haunt. That's not me, I don't think. But I think we need to be actually quite brave and find the middle ground and at least try and say something. And I think it's also acceptable, as long as things are done in a traceable way and it's understanding what has been done, to in a way build models that we find ultimately are wrong, but point to a possibility. And I'm sort of thinking of tipping points in particular, rapid change. Some models might indicate rapid change might occur, say, over the UK landscapes. Now that will guide us where to have sort of thoughtful measurement campaigns. So I'm not saying being deliberately wrong, but say something. The worst thing that would happen would be if, say, 30 years down the line, we've spent all our time in meetings like this, this is far too difficult, we can't pin down, we shouldn't be saying anything, and then the climate system does lurch or something unpleasant does happen, and people say, well, you at least had an inkling of this is going to happen, why did you not tell us? I don't know where that line, that middle ground, that sweet spot lies, but I think a bit of confidence that despite all the uncertainty, we can at least say something that is broadly right or an indicator of likely potential futures that will guide measurement campaigns. And the propagation of uncertainty, just how to illustrate it, illustration is such an important thing through diagrams and things like that, and I think just look in the IPCC. This is the standard plot, this is the global warming for the little numbers 32, 39, the numbers that contribute, it's just the spread, it's the amount of global warming. The bottom one tries to bring in climate about 2 degrees of global warming. The reason it's near 1 is these are normalised to the recent past. But just browsing through that, I think people have thought long and hard, obviously all the IPCC authors, about how best to represent things, and implicit in here is a lot of coupling, of course, in the models that contribute to this. So just quickly on is the world just simply linear? So some of you know I maintain this thing called Imogen, and the purpose of this is to see if there's linearity in the climate models, and there is quite a lot of linearity in them. And what I mean by that is, if you look at a particular season and a particular quantity, so southern UK rainfall in August, you will find that for 1 degree of global warming, in the climate model, you might have X millimetres per day increase in rainfall. For 2 degrees of global warming, you often find that there's 2 times X degrees amount of extra rainfall. And so what we did, and Peter and I developed this thing, is to do this, and we put it in these sort of anomaly patterns. So it's pattern scaled, and there's a massive assumption of linearity in there, which we find to some extent does work. And the reason for doing this is because it allows us to investigate other emission scenarios or other projections of atmospheric greenhouse gas concentrations that the models have not been run for. So it allows us to sort of fill the gaps between many modelling centres, because of the computational requirement, have only done a business as usual or 1.52 degree stabilisation run, so everything in between isn't there. But I'd only mention this for two reasons. First of all, the climate system might be highly linear. Of course, that makes it easier, and if we can scale our equations, that's even easier, because then you'll have a system, a reduced system, it's linear. You can quite often solve that almost semi-analytically. But what we did do with this is a funny thing, that we built this thing and it's actually been rarely used for trying different emission scenarios. But what it has been used for quite a bit is playing around with the land surface and different land surface configurations in the jaws at the bottom, and a lot of this work with Anna. And then we can see what the feedback is. So if you do something to the land surface, so you have say you believe it's more susceptible to ozone damage, or the opposite, that it might be respond higher than we previously think to CO2 fertilisation, you end up with more carbon on the ground. And so if we're given anthropogenic emissions, we can couple those together. If there's more carbon on the ground through the global coupling, the top right box, that feeds back on the climate and the level of global warming. So, but that was a coupling that is actually really very, very simple. I mean, you're just basically box counting across the land surface how much carbon you predict is going to be there and how that changes in time. But even that, just to get that effectively one number that was going back and feeding back on global delta T, it was surprising how much we had to test the code to make sure it was all right and correct. So is the world linear, or is it actually highly non-linear? So, of course, this is the example everyone knows, which is from the Lorentz equations, and this is where Lorentz tried to model, I believe, sort of convective behaviour in a stormy period, and tried to see how the rate of convection, so sort of updrafts, which are characterised by x, depends on both the horizontal temperature variation and the vertical temperature variation. Incredibly simple, right? I mean, it's just 3 coupled ODEs. I mean, how simple can that get? They're coupled. Now, that's the main point in this, is that so the x is a function of y. The second equation, y is a function of x, and there's a missing arrow there. It's also a function of z and y, and z is a function of x, y, x and y. So coupled system. You look at that, I think that'd be unbelievably simple to solve. It's not soluble analytically, but it is soluble numerically. So very simple set of equations, N3 is chaos. Now I reckon for a lot of the problems we've been looking at, we could actually get to some of these quite rich, exciting and interesting behaviours. And although we have to work for policy, I think it'd be nice to find a few months squirreled away to see if we can push some of our systems into novel behaviours, even maybe discover a new set of equations. So Lorentz, when he did that, he wanted to sort of take known conditions on a given day and run this thing forward to understand convection over the next couple of days. And so the dt term in the set of equations was just sort of 72 hours ahead. And so this was about 35 years ago, and set it going on what was probably in a ZX spectrum or something. Anyone remembers them? And it's sort of ticking its way forward. So he had these sort of initial conditions, and they were to 4 significant figures for x, y and z, put them in. Anyway, so he went off, came back, he'd been out for an evening, came back, there'd been a power cut where he lived. So, got to set it all going again. So it saved the numbers up as far as it got to before the power cut. And he went, I just can't be bothered to put these things into 4 significant figures. So he put them into 3 significant figures, set it going. And next morning came down numbers, of course, completely different. And it bewildered him. Why I've just changed this thing by 0.1%, and yet I've set the thing going, and a day of projection ahead, you're in a completely different regime. And so he was the first person to discover chaos, the fact that you can be super sensitive to initial conditions, and it was discovered allegedly because of a power cut. Now, of course, this sort of thing is people get very excited by, and people got incredibly excited here. And I came up here aged 18, unbelievably nervous, and somehow blagged my way through an interview very near here. But when we all met up, it was interesting. My tutor here, who I met the other day, it was quite incredible. She's still here. But 30 years ago, apparently, if you turned up at an interview and said, "Oh, well, I'm very excited in these non-linear butterfly plots," then you probably wouldn't get in the university. It's very sniffy about this sort of thing, non-linearity. That's changed a lot now, but very, very interesting. But despite all that, incredible. How can you just have 3 variables and get behaviour where just a slight change and you end up on the different wings of the butterfly? So there's some sort of consistency in it, and so you broadly know where you're going to end up. but you don't know where you can potentially end up. You know where you're probably not going to end up, but you don't know which of those things you're on. So I'd love to see if some of our work could lead to a new set of things like that. And having just said it, N is free, it could be as simple as what seems to me to be the three things we somehow need to couple together. And given we're talking about coupling, it's that little overlap. You can't beat a Venn diagram sometimes, but so, you know, can we offset CO2 emissions with trees? I feel that's what we've been charged with to answer Theresa May's question. Biodiversity, that's come up a lot, an enormous amount in some of the talks. And well, who knows what's going to happen to the UK over the next few months, but and beyond, but we've got to be able to feed ourselves as well. Right, so as some of you know, I do like books, and we get 25% off, so act quick, you've got 2 days left. Tell me Newton. But this book I bought, you can come and have a look, it's in my office upstairs. But absolutely remarkable. All of the stuff I've been showing about this non-linearity has been done, but very near to some of the things we've been looking at. What a great title. Behavioural rationality. There's been a lot about how do you distill down the rational behaviour of people into equation. That could be your X term. Heterogeneous expectations, well, yeah, it's all about scale and variability, and that's in there, in complex economic systems. Just bizarre. I mean, of course, book gets very near, so I'm quite sure we could almost take the equations out of some of the chapters in there and replace them with the variables that interest us, and take that forward. So yeah, do make the most of that. It's 25% off. So you can buy that for £18. Now, okay, so we talked a lot about linearity and talked a lot about non-linearity, and this is something that really Peter's been encouraging me and others to think about, particularly Peter, is, well, could we be in a situation that you're sort of in this sort of strange area between the two? So up until recently, we've nudged the system slightly as CO2 has gone up. We could end up, and there's reason to believe, you know, there could be quite dramatic in some of these global climate models, quite dramatic non-linear changes. Now, we don't want to go there necessarily. Almost certainly we don't want to go there, because society might not be able to keep up with the change. So, you know, the situation, you only change slightly more atmospheric CO2, and yet you see a runaway change in responses, or at least a very rapid, almost disproportionate change. So there is this thing called the DACOS toolkit, developed by someone called DACOS, and where as you get near to, you leave linearity and you head towards non-linearity, you actually find that your variance goes up, your autocorrelation goes up, and your skewness. So if you looked at a distribution of something you were measuring, temperature, ice cover, whatever it is. And I think there's a lot in this. And having talked about this thing about non-dimensionalization, and you only ever have two terms that balance each other. I don't know how you prove this, but I'd like to bet in the literature that the point where you get three terms balancing, so you're transitioning between what the dominant sort of things balancing each other in the calculus, this term versus here, this movement is all linked to here. So the idea of this is that it gives you some warning of what might be coming as you leave linearity. And I think a question which we could try and answer is, if you have lots of spatial information, so like Earth observing, does that allow you to see more about the system? Maybe regions are independent, but collectively it gives you, in effect, a longer time series. Or maybe it's even something about the spatial correlation between the variables, that you would see this sort of behaviour. You would, in effect, extend the DACOS work from these single time series to incorporate spatial data. Is that something that we could do, think about and measure? So, you know, we could go and look at the UK landscapes in terms of its response to imposed extremes, the sort of thing we've been seeing recently. Can we see this sort of behaviour? But the spatial variability gives you more information, and this is just a very sort of crude schematic to capture that. So are we heading out of linearity? We may not be in a new state, not because we've gone through some tipping point as we approach this transition. And this talk's meant to be about coupling. So what is there something about the couplings that if we got into that transition state and wanted to get back, we could get back? What would they have to do to the system? And again, is this thing that is it just the box models or not? So right, I'm nearly there. I realise we're going to. So as just a quick nice quote from Chris Dent. I thought this was superb. Somebody sent me some information. There's this strange logic in the world sometimes. If we couple models together, we automatically get a better product. I thought that's very good. Thanks. And I can't resist saying this is a bit of a joke. Don't worry, I'm not going to talk through all this because my talk's ended. But having got this confidence, you could get down to just free state variables, and perhaps we could distill the whole system down. And if we non-dimensionalized it right, we'd be fine and find the answer. And I said, could you just give me an example of how you see coupled models? So this is the sort of thing that came back. I'm not going to talk through it, but I mean, it's all about agricultural yields, farm emissions, ecosystem services. But coupling, what we're attempting to do is write equations, and as someone said, make every single one of those black links thicker. So I can't work out to be depressed by this or actually revel in the complexity. And you sent me another one. Yeah. The third one you sent me was so complex that I had to, even if I sat at my computer, sort of moved the slider up to 200%, 300%, I could just about make out the words and links. So you certainly wouldn't make it out here. So finally, one last slide. There's this whole thing called emergent constraints. Very briefly, if you look across climate models, something emerges, and it could often emerges, and I think this is based on often captures the coupling strengths between things, that there are common features between climate models that might link something you can measure now to something in the future, say fluctuations of temperature to equilibrium climate sensitivity. This concept is such that if you find these emergent constraints, then you can read off the data and refine the estimate of the thing into the future. So this has been talked about, but Peter will cover this more. By one line, has anyone ever found an emergent constraint, though, an intercomponent that actually captures the feedback? So up the left-hand side would be some key, say land atmosphere feedback, ocean atmosphere feedback that we're not sure of. Can the emergent constraint method pin it down? So in summary, we could potentially have a chaotic system. Is it non-linear? Is it linear? Can we get indications of approaching rapid change? Is it all too difficult because uncertainty balloons? Or could we actually say, come on, let's be brave. We do at least have some predictive capability. So to get us all talking, you can put the words on the web. There's these great Wordle things. If that helps. Well, thanks for listening. Sorry, it was a bit of a ramble in places. I think your talk was a lot better, really, actually. Thanks.
Brilliant.